Okay, we're continuing our work now on the fourth module in our chapter on magnetic field sources, chapter 28. This will be section 28.4, where we are going to discuss Ampere's law, one of the four fundamental Maxwell's equations. Ampere's law is given by the following equation. Although this is in vector calculus, I think you can follow what this is. That if we have a wire that carries or a length, and it carries a current I, this will have a magnetic field that goes around in this direction, then comes around behind the wire like this, in the manner of the right-hand rule. Okay, so now we've got a magnetic field B, a current I that flows in a wire. Now we could imagine now for a second that we take this as a long wire and look at this as a circle of radius r. And we can now say, well, let's integrate how much B there is all the way around this circle. So we're going to take an infinitesimal length, ds, and dot it with that magnetic field. They're pointing in the same direction. It doesn't look like it here, but they're pointing in the same direction. So I'm going to take the integral and add up the magnetic field dotted with the infinitesimal distance and see how much magnetic field there is all the way around at a distance out that's r. Okay, well, do I know the magnetic field out a given for an infinite wire? The answer is yes. For an infinite wire, we can write this as mu naught I over 2 pi. I used A before. I'll use R right here because I used R in the equation. Over 2 pi r. That gives us the magnetic field. Now we want to dot that, take the dot product of that with our distance ds, and we want to integrate that all the way around the circle. But this is constant all the way around the circle, so we can move our integral to here. Well, the integral of ds going around the circle is simply the circumference of the circle. We're adding up all the little lengths all the way around the circle. So in fact, what we get is this is mu naught I over 2 pi r times the circumference of a circle, which is 2 pi r. Oh, beautiful result, isn't it? 2 pi r cancels the 2 pi r, and we simply get the result here that the integral around this perfect circle for an infinitely long wire is equal to mu naught times I. So we get integral of B times ds around a closed circle is equal to mu naught times the current. Okay, now this is one of Maxwell's equations, but we need to do some work with it, as we'll see in just a moment, and understand what it was that Maxwell did that contributed to that. Now you can say, well, we used an infinitely long straight wire and we used a perfect circle to compute this. Yes, but what one can show is even if the wire curves in any manner whatsoever, and even if the loop goes in a very convoluted way, so here's our curve going around and here's our current I, it doesn't matter. You still get that result no matter what the curve is and no matter what the path is that we integrate around. You'll always get the same answer, and that's a remarkable result. And that's all we need to learn for this section. If the wire is on the outside, though, it turns out it makes no contribution. So we have to write this as the current that's inside. Now sometimes I ask a test question where we have a curve like this, and you might have 2 amps here, three amps here, both going through that loop, 1 amp here, and I say if I integrate all around this loop what is that total integral of B dot ds, integral of B dot ds around this whole loop? And the answer is I add up the currents that are inside. If there's another one over here, like 7 amps, it doesn't even count at all. It doesn't go through. But here I have one that goes 2 amps up, 3 amps up, so that'd be 5, but you subtract the 1 amp going in the opposite direction, so that answer would be 4. So on this problem, the integral of B dot ds would be equal to 4 times mu naught.